Great. Like Simon said, my name is Pearl Lee. I'm a research analyst at the Federal Reserve Bank of New York, and I'm here today to talk about how we at the New York Fed on the GSG team have used Julia's parallel computing to parallelize our own forecast step. And I'll be talking about what we've learned and kind of how we have tried to leverage Julia to do the kind of macroeconomic forecasting that we do. So to start, I'll begin with the standard disclaimer, which is that this talk reflects my own views and my own personal experience with Julia, and does not necessarily represent the views of the New York Fed or the Federal Reserve System. That out of the way, just to give a brief overview of how this talk will go, I'll first begin with a brief intro to GSG modeling for those who may not be familiar with it. For those who are, I'll try to keep it very short. I will next talk about what we call the forecast step on my team, so about what we're trying to accomplish and the challenges that we faced while trying to implement the forecast step. Next, I'll walk through two ways in which we attempted to go about parallelizing our forecast code, and then I'll conclude. So to start with, a DSG model, DSG stands for Dynamic Stochastic General Equilibrium. So it's a so-called micro-founded macro model. It's a model of the macroeconomy that's kind of based in knowledge from microeconomic theory about how agents optimize, how firms optimize, and how all of that behavior kind of coalesces into a general equilibrium. And so DSG models are used both in policy and in academia. They tend to be used for forecasting. Their advantage over other models is that they can be used to study counterfactuals and kind of understand the structural forces underlying past outcomes. And we also use them, especially at the Fed, to understand how monetary policy kind of ripples through the economy. So this is kind of a big slide, but basically we can represent a DSG model as a system of two dynamic linear equations. So the first one is what we call a transition equation, which kind of maps a time t-1 vector of latent or unobserved states to a time t vector of states, and also we incorporate shocks that hit at time t as well. After the transition equation, we have the measurement equation, which maps the current period's unobserved states to a vector of observed data variables, for example, GDP or inflation. And all of these matrices, these are both linear equations, so the T, R, C, Z, D matrices are all functions of some vector of time invariant parameters, which we call theta. So just to review the notation, ST is a vector of states, for example, some kind of notion, some economic notion of output growth and inflation. YT is a vector of observables, so these are things that we see in the data, like real GDP growth or core PCE inflation. The epsilon T vector is a vector of shocks, which hit in the current period, for example, a shock to productivity. And then the parameter vector theta is kind of the most important variable of interest, and so these are kind of time invariant deep economic parameters like the discount rate or some kind of long-term inflation target. So if you remember on the previous slide, the vector theta of parameters kind of determines how the rest of the state space evolves in the form of determining what these state space matrices look like. So at the New York Fed, we've been developing for the past about 2 years this package called dsg.jl, which we use to solve, estimate, and forecast DSG models in Julia. So for an excellent intro to DSG.jl and a discussion of kind of how we used Julia to different Julia language features like dispatch and the type system, I recommend you to Erica Miskowski's talk at JuliaCon last year. I think it's an excellent intro. I will be focusing specifically on forecasting and on parallel computing, but I think it's a great reference. So, but just for a brief overview of what the package looks like, we have as our main feature what we call a model object, which is some instance of a concrete subtype of the abstract type abstract model. And so this model object stores information about the model, including parameters, states, computational settings, and more. And so kind of how this works through Julia is we define these top-level model agnostic functions. So things like solve, estimate, optimize, all of these are defined for any subtype of abstract model. And then some of these higher-level functions will in turn call lower-level functions, for example, measurement, which will do dispatch and determine the appropriate method to use to return that model's specific measurement equation matrices. So for a very stripped down kind of version of what this would look like, we have a type declaration for type model 990. So you can see how we have this vector of parameters. We have some dictionaries that map the names of the states, shocks, observables, et cetera, into indices. And then we have some additional information about the model, as well as some computational settings. So there are actually many more fields, but these are kind of the most important ones. So given that we have a DSG model, what are we interested in doing with it? So there are two main steps, perhaps. So the first one is the estimation step, where we attempt to conduct inference about the posterior distribution of the parameter vector theta. Given the data, we ask ourselves what's the most likely distribution of those parameters, and given those parameters, we're able to, again, reconstruct those state space matrices for each particular theta. And so that part has already been done. That was discussed, again, in the talk last year. The next thing that we can do is the forecast step, where we take this distribution of parameters, this distribution of draws from the posterior, and we can use those draws to then get a distribution of past states, a distribution of future states, as well as many other things. And so that will be the focus of this talk, and in particular how we kind of did that using parallel computing in Julia. So to elaborate on the forecast step specifically, this is a little squished, but so to recap, in the estimation step, we generated a large number of draws from the posterior distribution of the parameters. And so for each draw, call it theta j, we can do a number of things. So if you're an economist and you're interested in this kind of thing, then this might be a slide that you really care about. If you're not, then feel free to kind of ignore it and just think to yourself, we do a lot of things with each one of these parameters. So for example, given a theta j, we can estimate what the most likely states throughout the history might have been. And the reason that we care about this is that these are unobserved states, which are kind of separate from the observed data. We can also iterate the state space forward to get future states, so we can forecast, again, given some parameter vector theta. In addition, we can compute what's called a shock decomposition, where we try to understand which shocks ended up driving the observed history of these estimated states. And we can also compute the response of each state to a uniform sized shock at time 1. So these are all kind of things that we want to do. Each of these are relatively computationally intensive. And it mostly just involves a lot of matrix multiplication, some linear algebra. So you can kind of see as we're setting up the computational challenges that we'll face when trying to do this for a large number of draws. So to kind of give a sense for what this looks like, again, recall that we have this distribution of parameter vectors drawn from their posterior distribution. And we can take that distribution of parameters and turn it into a distribution of estimated past and forecasted future states. So the black line here is the I believe it's the mode or the mean of the smooth states, the smooth historical states. And then you can see that once we switch from estimating to forecasting, we have this additional uncertainty about where we think the natural rate of interest is. So this is taken from our most recent blog post about forecasting the macroeconomy. So basically the goals in all of the goal in implementing the forecast step is to minimize both computational time and memory usage, which are, I think, pretty standard goals. So in the past, we started out with all of this code written in MATLAB. It was very old. It used to take about 70 minutes to run the entire full distribution forecast with a number of different settings. And so clearly this is too long, both in the realm of policy, where we often want to have results more or less immediately, as well as in academic research. You can imagine that when we're doing model development, we want to typically do a lot of iterations of different models and compare, so 70 minutes is too long. And similarly, for memory usage, since we have this high number of draws, we compute a large number of different products, all of which are kind of high-dimensional matrices. You can see how this might become a problem as well. So we can start with just the naive implementation of all of this. You can just imagine a for loop. We have all these parameter draws that we've gotten from the estimation step, and then we just loop through each draw theta j. And so for each parameter draw, we want to turn the parameter vector theta into these state space matrices, which will combine in this system variable. Then we'll estimate the historical states, we'll forecast future states, we'll do some other things, and then finally we'll write the output for that draw to disk, and then we'll do it all again. So clearly this is an ideal, and we'll talk about next about kind of two ways that we went about trying to parallelize this. So just to kind of skip to the end of the most important thing, which is the results. We did these benchmark timing tests around the time that we finished this step of the forecast code. So this is kind of before we switched to Julia 5. So apologies that it's still in Julia 4. So you can kind of see that for each step, the Julia code is quite a bit faster. In particular, for the full distribution forecast, it's about 5 times faster. So you can imagine it going from about 70 minutes to maybe like 12 to 15 minutes, which is definitely an improvement. So how did we do this exactly? We considered 2 approaches. So the first one was kind of using distributed storage through the distributed arrays package, which is part of Julia Parallel. And the other one is what we call a combination of PMAP and blocking. And I'll talk about why we went with the first one and why it ended up not being the best choice for us. So for those who aren't familiar with distributed arrays, it's a package that is meant to help you when you have arrays that are too large to be stored on one machine. And so you can basically distribute the storage of your large arrays across multiple processes. And then each array, or each process owns some local part of the process. Each process operates on the local part of the array that it owns. And so you can see how this might lead to like a natural way of parallelizing your code. Each process owns a certain amount of the array. Each process does operations on that part of the array. Seems great. So just how this looks in practice, we add some processes. We load the package distributed arrays on each one of them. And then we'll call this initialization function drand, which just initializes a distributed random array of random floats. And we want to, in particular in this case, we'll distribute our random array across the second dimension. So what that looks like is if we query the first worker process for its local indices into this new array, you'll see that it owns, so it's a 2 by 25 by 2 array. So it owns basically the first 5 columns, say, of this big array. And then we can also equivalently query that worker for its local part of the array, which looks like this. And then we'll finally just remove the worker processes. So this kind of already suggests how we might do this in the forecast step. But to be very clear, what we want to do is take these parameter draws, these typically 20,000 parameter draws, and we'll distribute them among some number, typically 50, of worker processes. And each worker process will kind of handle doing everything for the parameter draws that it owns. And then this will involve implementing both these lower level functions, which operate only on one draw, as well as these higher level functions, which usually have this _all, which will kind of take many draws and call the lower level function on each one of them. So this all seems very natural so far. You can kind of imagine how this would go. We'll add these processes. And now all of our functions, load draws, prepare systems, filter all, smooth all, forecast all of these things kind of take in distributed arrays and return distributed arrays. And so all of these computations that happen under the hood, again, are supposed to happen on whatever process owns the local part containing those draws. So this seems great so far. So the first disadvantage is that by using distributed arrays, we kind of have to explicitly assign parameter draws to different processes. And the way we do that is kind of by deciding along which dimensions we split up the relevant parts of the array. And so one consequence of this is that we actually have to divide the distributed arrays evenly among the processes. So this kind of creates a very basic problem where if we have a number of draws that's not divisible by the number of processes, then we have a problem and we can't do anything except throw out the other draws, which definitely isn't ideal. And a second disadvantage is just that distributed arrays are actually very hard to construct. The syntax is a little bit unwieldy. And furthermore, you have this function init, which is the first argument to this darray constructor. And each call to the init function returns only one darray. And so you can kind of see how this might cause a problem, since we often, we and I imagine many other people often want to return multiple return values from a function. And so in particular for smooth all, for example, we want to return 4 different darrays corresponding to the different types of smoothed things that we return. And so what this ends up looking like is just very ugly code. In fact, it's so ugly that it doesn't fit on one slide. So it'll be on 2 slides. So basically the important thing to get out of this is that since we can only return one distributed array from this call to this init function, well, what we ended up doing at the Fed was we decided let's just pack all of these different outputs into one distributed array, call the init function, and then kind of unpack them later. So this is basically what we're doing. So this init function takes a tuple of local indices and returns an array corresponding to the local array living at those indices. And so we call smooth this lower level function. We get these 4 outputs back, and then we kind of just pack them into this part of the local array. And then at the end, we have this local array, which has these 4 outputs kind of just stacked on top of each other. And then we kind of index them out, and then we get 4 distributed arrays. So for a visual aid for what this looks like, we just return this big darray. And you can see that since not all of the outputs are kind of the same size along the one dimension, that we have a lot of wasted space right here, which is bad. It's all kind of bad. So maybe those things together aren't the worst thing, but then the worst thing perhaps is just that in practice the computational time wasn't really much of an improvement over perhaps the naive implementation. And so this is because it's actually very difficult to reallocate different parts of a darray from one process to another. There's no natural way to do that. You'd probably just have to do it through the darray constructor. In practice, some compute nodes are busier than others. So we at the Fed have this Linux cluster with 24 cores on each compute node. We have 10 compute nodes. So when you add these processes, our scheduler submits those processes to various compute nodes. And then perhaps we're midway through a computation, and then some other economist on the floor submits a lot of jobs, and they end up clogging up one particular compute node. So that's kind of already that's happened basically after we have any control over where the processes go or anything. And so what ends up happening is this bottleneck effect, where since we have to have smooth all return before forecast all can begin, you're kind of limited by the compute time of the slowest process on the slowest compute node. So here, given all of that, what we'll do now is kind of talk about how PMAP plus blocking comes to the rescue. So like I said, we typically have about 20,000 draws. And what we do in this step instead is to kind of divide them into blocks. We'll read in one block at a time, do all of the computation that needs to be done in that block, and then using PMAP. And then when PMAP returns, we'll write that block's output to disk and then continue to the next block. So this all, again, suggests a very natural way to write the high-level code. So we'll just iterate through the blocks. For each block, we'll load the draws for that block. We'll call PMAP on this function called forecast1draw, which just computes all of the desired forecast outputs for your one parameter vector. And then once PMAP returns, we'll write the results and then continue to the next block. So for an example of how forecast one draw works, it basically looks like the inside of that naive implementation. It looks like the inside of that for loop. So again, given some parameter vector theta, we can update the model to compute the state space matrices given those parameters. And then we will just do all the things that we wanted to do before. So we'll estimate what the states were throughout the history. We'll forecast future states. We might want to, compute shock decompositions, do all these things, and then what we'll return is this dictionary just mapping the names of the things to the actual arrays themselves, and we'll return that. So why is this better than using D arrays? Basically, so to address the first problem was kind of like the manual assignment of parameter draws to different worker processes. That happens automatically through PMAP. And furthermore, since this is all being done kind of dynamically, one draw at a time, if one process on one compute node is busier than some other process, then it will return more slowly. Other faster processes will get assigned more draws. So this kind of also all happens under the hood away from the user, and you don't have to worry about it. Furthermore, you can kind of ditch all of those higher level functions which had to deal with handling multiple draws. All of those were basically boilerplate anyway. You kind of did the same thing, but you called different functions underneath. So we can just throw those out as well. And finally, we can kind of take advantage of the implicit independence of these different parameter draws. So if I have one parameter vector, theta j, computing those forecast outputs for that parameter vector doesn't depend at all on what any of the other parameter vectors are. And so that wasn't something that we had fully taken advantage of under the DRA regime. And so finally, because we're computing in blocks, we kind of reduce the amount of memory usage that, the amount of memory that's used on the originator process when PMAP returns. So, and of course, we're able to kind of flexibly adjust the number of blocks that we do at a time in order to kind of to manage that memory usage as well. And so basically the result of all of this is that we end up with code that is more natural, more readable, more efficient, and most importantly, in my opinion, more beautiful. So just to conclude, so this was kind of a big step for us. This was our version 0.2.0. So long term, what we want to do at the New York Fed and with this package is, first of all, to make it less specific to our specific computational needs. So currently, DSG-JL is a registered package, but I don't know of anyone who uses it besides us, and that's at least partially because it's hard for people who are not us to use it. And that's because our documentation, of course, can always use more improvement. And there are also just some features that we use, for example, like doing these population adjustments that not everybody needs to use or wants to use, but that doesn't work. Like the code doesn't work if you don't have population data, for example. So that's definitely one thing that we want to do is to kind of make DSG-JL more accessible to the broader community. Another thing, it actually took us quite a long time to move from Julia 4 to Julia 5, and of course now everything's kind of accelerating, and we're already on Julia 6, and Julia 1.0 is supposed to be coming out now, so we definitely need to continue to keep up with the pace of Julia releases. And then finally, I think we just generally want to be, to try harder than ever to be responsible contributors to the package ecosystem. I know our build right now is actually failing, which is a little embarrassing. So there are things like this that we, I think, as people who work at this policy institution, maybe don't focus on as much that are kind of important to being members of this community. So. And then so some work that we're doing right now is includes forecasting under possible alternative monetary policy rules. So this is like an interesting exercise that we like to do for policy analysis that is not currently implemented in our Julia code. We're writing a paper about evaluating past forecasts and across different models and trying to understand what caused the changes in these forecasts. And finally, our summer interns are working on estimating nonlinear models using the tempered particle filter algorithm. So that'll be an exciting development that's hopefully near or at the frontier of the kind of econometrics that we do. So there are a lot of people to thank here, including everyone who's worked on this package at the New York Fed, including Erica, and as well as our collaborators at QuantEcon, including Spencer, who's giving the next talk in this room. So we're very grateful for all the help we've gotten, and we're excited to continue working on it. So thank you so much. Are there any questions? Yes.
Would you mind going back to your PMAP slide?
Yeah. Is it here or?
No. Yeah.
Oh.
When you were doing your PMAP analysis, did you look into any of the other options with respect to PMAP, like blocking size or cache pools? And if so, what did you do?
Do you mean the batch size?
Yeah, batch size.
Yeah, so I think, as I understand it, that's something new in Julia 5, and like I said, we really only very recently moved to Julia 5. I did try using the batch size keyword argument, although I think since this function forecast1draw returns a dictionary, I was having some kind of like type assert issue with that I haven't yet figured out. I literally just tried this like a week ago, so that I have not had any success with so far, although I have tested it on smaller examples. I'm not familiar with caching pools.
Yeah, I just like that.
Yeah. Yeah, I'm definitely less familiar with those. We did also try using parallel for, which I think for other reasons is not ideal for our situation, since those the function that you call parallel, each iteration of a loop, of a parallel for loop, is designed to do relatively little work, whereas PMAP I think is optimized for where each call does relatively more work.
And your performance results, was that with the D array or was that PMAP?
This was a PMAP.
Okay,
Yeah. Yeah. Spencer?
Are those results relative to a parallel MATLAB code?
Yeah.
Using the same number of processes and everything?
Yeah, for 50 processes operating on the same cluster, we kind of did this like randomized submission to different compute nodes and averaged over time. So this was supposedly as fair as possible. Yes.
So you're estimating a state space model as an average. About how many parameters do you find in 20,000 iterations?
Yeah, so I think we have 95 parameters, not all of which we estimate. We maybe estimate like 80, maybe. And so we actually, we do 100,000 parameter draws, and then we thin by 5, I think, typically, because we use an MCMC algorithm, so there's a lot of serial correlation that we try to avoid. I think we might actually do some additional thinning after that. So, yeah. Yes. Sorry, could you repeat that? Sorry, could you just repeat that one more time? The MPI?
Are you using MPI under the hood to do the parallelization?
No, I don't believe so. Although I'm not familiar with MPI, to be honest.
You're just
Yeah.
using the built function.
Yeah. Yeah, and an SG scheduler. Okay, great, thank you.